how in the world do we get from A to B at the molecular level?
So here's the game plan. We're going to walk through this whole thing in 5 parts. We'll meet the molecules, see the key switch that makes it all happen, watch the atoms do their thing, then see how it's done in a real lab, and finally, how we prove we actually did it.
First up, let's introduce the stars of our show. Every great story needs its main characters.
Okay, so this is where it all begins. Aniline. It's our starting material, our foundation. I like to think of it as a block of marble, you know? It's got all the potential, we just need to shape it.
And this is our masterpiece, our finished sculpture, acetanilide. This is what we're aiming to create by carefully modifying that original aniline molecule.
Okay, now for the really cool part. What's the big idea here? How does this actually work? Well, it all comes down to a really clever and powerful chemical switch. The magic word for this whole process is acetylation. That's the key. It's kind of like we're doing a performance upgrade on our molecule. We're adding this new part, called an acetyl group, right onto the nitrogen atom of the aniline.
But you might be asking, where do we get this acetyl group? It doesn't just appear out of thin air, right? Nope. We need a delivery vehicle, and for that, we bring in our second ingredient, acetic anhydride. Think of it as the delivery truck carrying the exact part we need for the upgrade.
All right, let's zoom way in. Time to see what the atoms themselves are actually doing. It's like a carefully choreographed dance, and it happens in a few lightning-fast steps.
So, the music starts with something called a nucleophilic attack. Sounds intense, right? But it's actually pretty simple. Think of it like magnets. An aniline's nitrogen atom is electron-rich. It's got some extra negative charge. Acetic anhydride has a carbon atom that's a little electron-poor, a bit positive. And you know what happens? Opposites attract. That magnetic pull is what kicks the whole thing off, bringing the two molecules together.
So that initial connection, that attack, sets off this super-fast chain reaction. You can see it here. First, a tiny hydrogen atom, a proton, just kind of shuffles over to a new spot. Then boom, a piece of the old acetic anhydride molecule gets kicked off. After one last little tweak, everything settles down, and we're left with our super-stable new molecule, acetanilide.
And this whole dance has a name, which actually makes a ton of sense. It's called an addition-elimination mechanism. Why? Because first we add the two molecules together, and then we eliminate a piece to get to the end. See? Pretty logical. Okay, so the theory's cool, but what does this look like in a real lab? Let's get out of the diagrams and into the flask.
So here's how it goes down. You put your aniline in a flask, and then you start adding the acetic